Hello. Good morning. My name is Peter. I'm with the programming committee today. I'll be introducing our first speaker, Puneet Khushwani, all the way from India. Really brief bio. The ethos of Puneet's career has always been never stop building. The first part of his near decade-long career was a crazy roller coaster ride where him and his team built several products. In 2020, Puneet joined Coupa, where he transitioned to an engineering manager role. Please give a really warm welcome to Puneet.
Thank you. Thank you. Thank you. Hello, mic check. People can hear me all fine? Thank you. Let's start. Welcome to RubyConf. Welcome to this talk. I am Puneet, and the title for this one would be Finding Needle in the Haystack, Debugging Performance Issues. As they said, I've traveled for this talk all the way from Pune, India. This is my first time to the United States, and I must say, it's a beautiful country. I'd like to start off by doing Namaste, which is a very important part of our Indian culture. We respectfully greet people by bowing down to them like this. So Namaste and welcome again to this talk. A brief about me before we get started. I've been in the industry for about 10 years now. That probably justifies my gray hair. So over these 10 years, I've changed my job only once. The first employer, I spent around 6.5 years with them. Those 6.5 years was a pretty roller coaster ride. It was a startup kind of environment, building different products. We started with e-commerce, then we did some private label furniture, then we did a social media app, Instagram stories, like app back in 16, 17. Then we did something in the crypto space, 18, 19. You're trying to be the Stripe for blockchains. You're trying to be building token economies back in 18, 19. All of these four were very unique experiences, but they were all like a 0 to 1 kind of journey. By 1920, I sort of realized that I wanted to be in a company which was already at, let's say, a 10 and do my bit to take it to 1,000. And I decided to move on and join Coupa Software. Over the last 3.5 years with Coupa, I've transitioned from an individual contributor role, and I'm a manager now. I support one of the platform teams from Pune, India. A bit about Coupa. Coupa is the leader in the business spend management industry. We help companies save money by enabling them to spend smarter. This image, I'll not go into a lot of detail, but it has some of the portfolios of our product. We start with procurement, then invoicing, expense, pay. We are doing something with community.ai, and doing pretty cool there. So on the technology part, Coupa is probably one of the largest monolith applications that still runs on Ruby on Rails. A lot of our code is still on Ruby on Rails. We have hundreds, maybe close to thousands of developers who contribute. And in cases like these where the teams are big, it happens at times where accidentally some code gets merged, which causes performance issues. Now the time that they show up, it depends, right? They may show up, somebody may see them a week after, a month after. To go back in time and to see what caused those issues is literally finding a needle in the haystack. Today, we'll talk about a systematic approach to how to go about it. A brief agenda sort of thing for my talk. So we'll start with the importance of measurement because unless you measure performance, very difficult for you to track it. Then we'll talk about some key concepts in this space, profiling, benchmarking. Then we'll talk about some profiling tools. There are a lot of different kind of tools available. We'll talk about when to use what and how they help us in general. Then, most importantly, in the second half, we'll try and cover some of the issues that my team at Coupa had been seeing in the last year or so, and how these tools helped us get over it. But before I get there, any Bollywood fans? So I see a show of hands. So we'll start off by this picture, and I want you guys to tell me what is the difference between this one and this one. So I'll again, maybe this one and this one. The lady, beautiful lady is missing. The men are more happier, they're enjoying their time. But the difference that I'm trying to highlight here is seat belts, right? So seat belts, they save lives. They literally do, right? And if you see this car, this is a much faster car, it's a racing car. A lot is at stake here. Hence, there is more safety. The seat belts here are better. So the faster the car is, the safer it has to be. In that context, in which we work, software, right? For software, processes are like seat belts. I in fact did a whole talk for RubyConf India a couple of months ago about 5 processes that we have at Coupa. One of them is this, that I like to talk about a bit here. This process is about measuring performance, right? Because unless you measure performance for yourself, you will not be able to track and you will not be able to find degradations, and then the customer may end up reporting them for you. You don't want that to happen, right? So you need a very systematic process in which you, let's say, sprint over sprint, week over week, or whatever time that suits you, systematically measure performance. How do you do that, right? Locally, there is no point. On a QE instance, there is no point. You need to do this on an instance which has production-like data, which is having a production-like stack, production-like hardware capacity, and you need to test it on production-like load, right? So production-like data, production-like load, and production-like hardware. If you do all of that, you get a realistic picture of what your software is performing like. And then you measure this against your benchmark, against your baseline, sprint over sprint, month over month, week over week, depends. And then if you see degradations, then you need to flag them already, because you don't want your customers to flag them for you. Very important to start here, measuring performance. Now, let's say the performance team comes to you and says, hey, this background job is, let's say, 30% slower, right? How do you go about it, right? In legacy software applications and in general, right, your code may be going through a lot of legacy software. It may have a long chain of methods that you may not have an idea about, right? And it makes it debugging more challenging. So profiling comes to our rescue. And what is profiling? Profiling is a step-by-step accounting. It's a step-by-step accounting of the relative resources consumed by a program's subroutines. In simpler words, a big program, let's say, has 10 methods. You want to see some magic that tells you which of those 10 methods is probably slow, right? That magic is profiling. And when you have that data, it may be overwhelming, and you literally need to go with a microscopic thing and then see what is there. As an example, let's say this simple background job. It has method 1, 2, 3. Method 2 does nothing but sleep for 10 seconds. This is my slowest piece. I want some magic to tell me that method 2 is the slowest. This is one of the profilers that one can use to tell you something like this. I'll talk about it in a detail in the next slides, but this is a magic that shows me method 2 is taking most time because of sleep. This is profiling, guys, for you. The next one is benchmarking. Again, very, very important, because from the last slide we got to know that, hey, method 2 is slow. Now you will make attempts to optimize method 2, right? but you don't want to merge it to master, wait for the next performance testing to happen. It may again take weeks for you to get the report, right? You need a very structured approach via which you benchmark and compare your changes. So again, there was a method 2, sleeping 10 seconds. Somebody went, optimized it. Now it takes 8 seconds, so I have a sleep of 8. And now, I typically it's a trade-off, right, between the memory allocation versus time. So I have more memory allocations here and less time. I need a systematic approach to measure, benchmark, and compare this. People can use something like this, benchmark IPSA. That I personally have been using, and it's quite very interesting. As you see here, the most important thing here is the config. It says 100 seconds you run this thing for, and warm up, right, is important because as all of you would know and agree that software, when it runs for the first time, it is normally much slower, right, because it is loading up a lot of things. It's booting up in that sense. So we need to ignore the first few iterations of our run and exclude them from our comparison. And in the remaining parts, I'm just doing comparison. And it shows up a report like this. A very interesting part of this is these allocations. As all of us would know, memory allocations are of two types, allocated and retained. So yes, your program will obviously allocate memories, but if it is retaining them after it exits, then it is something for you to go back and check. The retained memory should ideally not be much. If there is, there may be reasons, but you need to definitely go and check why it is retaining memory. In my case, 0 retentions. It gives me a kind of boilerplate of my allocations. Then warming up, it excludes these, and then calculations, and then comparison. It tells me my slower is so much slower, my faster is so much faster. These systematically help you to have a shorter feedback loop. Because you make a change today, you don't want to wait for 2 months or like to get. So this helps you get earlier feedback. Now we'll talk about profiling tools. These are very different kind of tools available in the industry. We'll talk about some of them, and then we'll talk about how they help us. Statistical profilers. These are very interesting in that sense because they, from the outside, will take snapshots of the call stack at a given interval of time. They, from the outside, will take snapshots of the call stack in a given interval of time. They'll collect that data and present it to you. I think all of us know what call stacks are, but I'll just take a bit to talk about what a call stack is. So if a function A is calling B, B is calling C, C is calling D, while D is executing, if you look at the call stack, D would be at the top, and then C, and then B, and then A. So basically, that is a stack. That is the call stack. And these profilers from outside will take snapshots of that over time and then report back. They work in two different ways. One is you need to add an instrumentation code around which you need to pass your code. It's basically a block of code within which you put your code which you want to profile. StackProf falls in that category. The other category is RubySpy. It does exactly similar thing, but you do not need any instrumentation code. You can attach it to a process. You can attach it to a process by giving a PID. To understand how this works, I've sort of complicated the previous example slightly. Now we have 3 methods. Method 2 is shorter, takes 5 seconds, and there are multiple calls also. So let's say if we are to run StackProf on that, how would you do it? This snippet helps us to do all of that. The important thing here is this mode, right? There are 3 modes that this allows. The first one is wall time. Wall time is the end-to-end time. End-to-end time. CPU time is the time in which the CPU is engaged, the processing time. In my case, because I'm doing nothing, I'm just sleeping. So CPU time would be close to 0, but wall time will have the 5 seconds and the 10 seconds of sleep included. So you need to decide what do you want to measure, wall time at some cases, CPU time at some cases. It's a call that you guys have to make. Then the third one is object. This can also be used to check allocations by your program. And then this is how you use it, and output of that is something like this. Pretty nasty in that sense, but I'll try to explain it. There are two things that stand out here. One is the total section and the other is samples, right? Now total section will give you a representation of the number of snapshots or the percentage of snapshots in which this method was in the call stack. This method was in the call stack. How many percentage of times? This is what the total would represent. And samples, it would represent the percentage of iterations when it was at the top. When a function is at the top of the stack, you can assume that that function is actually executing. In my case, because most of the time was by sleep, so sleep clearly appears 100% in the samples because it is the only function that was doing something. Everything else was a wrapper function. Everything else was a wrapper function. If you see here, bottom of the thingy, it shows up here, method 2, 83% of times in the total stack because it was taking around 10 seconds of 11, which is around 83%. So this tells us that method 2 is calling something which is taking time, and this tells us that it is sleeping and which is taking time. Now, as I said, these can get very hard to digest of just seeing this raw data, and hence there are tools available to better visualize this data. This one is a flame graph that people generate out of that JSON data, and this is backed by the SpeedScope website. It has multiple views, as you see. It has time order, left heavy, sandwich. This is the time order view. It represents the sequence, it represents the chronological order in which your program was executing. So started with method 1, then method 2, method 2, method 2, and whatever. So this is the sequence in which your program was running. This is a different representation. It sort of cumulates multiple calls of a method and aggregates that data. So if you see, method 2 appears only once here. 83% is what you saw in the first slide. It's almost same here. A different view. So it depends on like a person to person. Somebody will love this, somebody will love that JSON, but these are ways in which you can visualize the data. So that was statistical thing. And these tracers are a different kind of profiling tool. Tracers work very differently. So tracers will literally inject themselves into your code and they will observe every single thing that is happening inside your code. Every single thing that is happening inside your code. They'll log that, they'll capture that, and hence these tracers have a very significant overhead. If your program takes 5 seconds, hypothetically, with the tracer it may take 8, 9, I don't know, it may take a much long. So RubyProf is one of the, so why do we need this and why they are different, right? The statistical profilers, because they take snapshots at a frequency of time, they may not be able to capture some nitty-gritties. If you need to capture those nitty-gritties, this kind of tool is what you need. In my case, it was simple, so it represents the same kind of data, but in a different structure and different format. This is the call stack visualizer. I'll talk about this in a bit in my subsequent slides. This covered the academic part of my presentation, and now we'll talk about some real life examples that our teams at Coupa had to face and debug, and how this helped. But before I go there, this is a very powerful quote by Mr. Albert Einstein. It is about the importance of curiosity, right? And it says curiosity exists for a reason. He said that he has no special talent, he is just passionately curious. When it comes about debugging these kind of performance issues, one has to be curious, right? Because without being curious, you will not or you may not be able to get to the root cause of it. And apart from being curious, you need to also have the right kind of mindset when it comes to these issues, right? Because you don't want to be having a feeling that, hey, why me? I was happy doing my feature development. Why are you pulling me into all of this, right? You should be taking these as learning opportunities, as I always say to my team. Learning opportunities. They'll teach you something that you may have not seen in the past. Okay, so first example. It is of a case where my DevOps team was seeing a job. So we have our workers for async processing. One of those workers who was doing async processing, they saw was stuck. They felt it was doing nothing. It was just stuck. And while it was stuck, it was consuming a lot of memory and it was not releasing that. That is the observation that the DevOps team bought. And they didn't stop there. They, by themselves, used a profiling tool, which is GDB in this case, which works by attaching a process ID to it. A small disclosure, so GDB is sort of risky on production environment because it will stop execution of your program. It will stop execution for your program. So you don't want to run this on a production like system. But in our case, they were absolutely sure. They just needed it for 5 seconds. They went, they gave the PID, and they took this snapshot of the result. Now, without doing anything, just 5 seconds of time, they were able to get this magical piece of information which was able to tell us that it was doing regex matches on very complex data in loops because there was a need to. And it was not stuck, it was doing something. So this regex we found was the cause. And you are able to optimize this to get a significant boost. But the point is, without doing anything else, you get to this. Imagine without these tools, very difficult to get to all of this. The second example is app boot up time. Again, they came up with this thing where they said multi-fold increase in app boot up time. Because we have so strong infrastructure of performance testing, we are able to catch all of this in the development phase. In the development phase, before it goes to production. So why is app boot up time important? It is because on production you want your processes to boot up sooner, and on development you want to give better experience to your devs. No dev wants, hey, it's taking 10 minutes to boot up your environment. Nobody likes that. So yeah, boot up time is a very important metric that we capture. Now, how did we go about it? Right? So typically when you do a bundle exec, Rails as environment production, you get a PID. Right? They use that PID with RBSpy. And they were able to generate these kind of flame graphs without making any line of code change. They compared these flame graphs between our baseline, which is sort of a trusted, stable thingy, and master. And they were able to, maybe hard for you guys to see, but they were able to point this as the difference. This was a recent piece of code that some of the team had added because they had to set some class variables. But this, they also didn't knew that will take so long. More debugging, sort of told them that, hey, not a lot of this is required. So they were able to optimize this very clearly. But again, without any code changes, you exactly know what is causing the problem. This really helped us again. This one is probably the most interesting one that our team saw. So everything in the application, okay, every transaction in the application, it became 2x or 3x slower. And this comparison was done after a 2 or 3 weeks of period of time. So obviously, in a company as big as ours, hundreds of PRs were merged. And now I'm on the platform team. We are the first responders to all of this. So hey, they come to me, hey, everything is low, try and figure out. I said, fine. This sounds to be unrealistic because what can one do which causes this to happen, right? But no, this was a fact that our team had to investigate. I started uh, with, with, with seeing the commits, and one commit was an outlier in which we were upgrading Ruby version from 2.x to 3.x. So before I go into my further slides, it's a disclaimer. So this is not about 3 being faster or 3 being slower, 2 being faster, 2 being slower. No, it is not about all of that. All my slides which will follow will be in context to how we were using this in our application. So I started to, how did we narrow down to this, right? So we basically did a commit before this upgrade, and we did this after the upgrade. So we had 2 commits, and then performance team did some testing, and they were exactly sure of, hey, that this commit is when the regression was caused. So we were absolutely sure that this is the commit that we have to figure out why. Then we started to look around of what data points do we have, because data is helpful. The first thing, as you see, is by our APM. Our APM said, hey, the heap size increased from, let's say, 7 dot something to 9 million. It also said that the garbage collection frequency had a significant spike. Object allocations also had a very significant spike. Then we did some profiling using something like StackProf for one of the transactions which went slower. It also reported that 63% of time was going into garbage collection related activities. 63% time. So all of this made us realize that there may be something because of which the garbage collection settings that come with the language, we may have messed them up. So there are variables that all of you may know which you can tweak, environment variables using which garbage collection is configured. So we first started to go and check those variables. Are there any new variables introduced in Ruby 3? Are we still using them? Are we still applying them on our stack? That's the first place when we started. It did some benefit, but it did not give us what we were expecting. So that was ruled out. Then we continued this investigation, and by now we were running all of this locally. So locally, Ruby 3 was much faster. It takes lesser amount of time. But our observation from the earlier APM data was that it is allocating more memory, and thankfully for us, we were able to see that even on local environment, that this was taking more memory. Then the game started. We're trying to figure out what is leading to these extra memory allocations. We used the profiler this time on the memory mode, and again it gave big pages of data that we had to compare with our eyes. But this highlights the difference between those two. It said Marshall, because of marshalling related stuff, these allocations came into picture. So we're like, fine, what happened because of which this all is happening? So we basically had 2 work streams by then. One work stream spent some little time to see if we can, remove Marshall. It was very, very ambitious for us to think that, but and use other options like message pack or OJ. Very ambitious thought. When things are bad, you really think out of your mind. So very ambitious effort we tried to make, but it was a lot more of work. So we came back to basics, right? And what changed in our application, in our configuration, that was leading to all of this. So for that, we needed to figure out that from which workflow are these new Marshall activities are getting called. For that, this is a thread profiler, and this is a call stack visualizer of that thread profiler. The good thing is it sort of said around 70% of time was in inflate. Inflate is from the caching flow. So as you all know, caching, when you cache something, because you want your cache to be optimized for space, you compress data and then you put it into cache, because these are big Ruby objects. You compress them first and then you put in the cache. But somehow it led to all of this. So far we knew that it is because of some caching kind of activities, extra Marshall that you are seeing. So we then went back and we saw, hey, what is happening? And then we saw our commit, the Ruby upgrade commit with finalize. And then we saw that we had upgraded DALI towards 3.x also in that commit. It was because the older version was not compatible with Ruby 3. So we had to change this DALI version. Then we started to see, hey, what changed in DALI in that version 3? So they said breaking changes. We are like, fine. So they said they replaced DALI with memcache store internally, and they did some changes to compress. And now the compression was true for larger values by default. So because of these changes and the way we had configured our caching engine internally, it happened to be like we were compressing the data twice. The value in memcache was obviously compressed, but the in-memory representation of that data was again compressed. We were compressing twice. Because of compressing twice, we were deflating or uncompressing twice, which was leading to all of this. So we're like, probably, hey, found it, so happy. But we spoke too early. So with this, we definitely got that performance. The time with these changes went back to baseline almost, but what we saw was a significant increase in the volume of writes to our memcache server. A significant increase in the volume of writes to our memcache server. That was because when we debugged, we understood that in the attempt to stop compression twice, we made a change which stopped compression absolutely. So yeah, we got a bit. So then we made more changes, and as always, we tested them very thoroughly. We were, playing with telnet, and we were actually seeing what data is going to the memcache, what data is coming out of the memcache, what is the in-memory representation of that data like. We did all of that, and we had to make some changes in our configuration. It was our configuration, it was not any of this, it was a configuration that we had to change to get back performance, and with this, we were happy. So key takeaways, right? We started this talk by some academic content, some concepts, measurement of performance, very important. Without measure, you cannot know what to profile. Till you know what to profile, you cannot benchmark because you don't know what is the slowest piece that you need to optimize. So measure, profile, benchmark, and then we spoke about some kind of profiling software, StackProf, the concept statistical profiler versus the threads or the other kind of profiler. And then we spoke about how all of these tools helped us in real world to save developer time. So yeah, what I want you to take back is in 30 minutes or 40 minutes of time, it is practically impossible for us to cover these into a lot of detail. So the idea of this talk was to give you boilerplate, high-level view of what exists. You can go back and see what will be useful to your use cases. The other takeaway I want to give back is again this quote by Albert Einstein, sir. It says, when you're trying to find a needle in the haystack, do not stop when you get the first one. Right? Keep looking for more. Keep looking for more. As we didn't stop our investigation. With the first change we made, we continued testing, and we figured out that that was not the best thing to do. There were other places that we had to solve this problem. So please, as a takeaway, when you are doing all of this, don't stop on the first one. There may be more needles, maybe better ones for you to go and fix. This is the last slide, and this is a very, very powerful quote that has helped me also. It says, we make a living by what we get. We make a living by what we get, but we make a life with what we give. And Ruby community is always there for each other. So thank you for all that. And I flying away all the way from Pune, India for this talk is my bit to share our learnings, experiences in this community. With that, that's my time. Credits my team at Coupa. There are a couple of Rails talks that I saw for the first half that inspired me to come and give more insights into what we see in the company. And Mike is here. He is my mentor for this talk. Thank you for that also, Mike. And thanks. So that's it.